Good morning, dear colleagues. I am pleased to present our joint research on intelligent system and technology for optimized object placement in medical and biological applications. The use of intelligent system in medicine and biology is becoming increasingly important. These systems improve accuracy, streamline operations, and enhance patients' outcomes. They can address a wide range of practical problems, such as the strategic position of surgical instruments, optimal sensor placement, and diagnostic image analysis. Our research focuses on the development of an intelligent system designed to optimize the placement of geometric objects in various medical and biological applications. Specific examples include hammer knife radiosurgery, placement of therapeutic targets, uh, laser coagulation, optimizing laser spot arrangement, bracket therapy, position of radioactive seeds, chromosome territory modeling for understanding spatial organization. To achieve this, we propose a universal mathematical model that can simulate all these processes. This model is based on the five functions method, which allows for the precise control of objects placement and orientation. By adjusting the model's parameters, users can simulate various scenarios, ensuring optimal placement and minimizing adverse effects. This approach transforms placement challenges into the framework of mixed binary nonlinear programming. The foundation of the proposed intelligent system is a universal mathematical model designed for optimizing geometric object placement. This model uses uh, specialized functions called phi functions to construct a generalized nonlinear optimization problem. We consider objects with specific metric characteristics. Their location in the Euclidean space is defined by coordinate set angles, which specify their positions and orientations. The placement regions also has defined metric characteristics. Objects should be packed in the region in one of two ways: at minimum distances, ensuring objects are placed at minimum allowable distances from each other and to the boundary, and by controlled overlap, allowing objects to overlap or extend beyond the boundary regulated by specific parameters. Our goal is to select a subset of objects that can be placed within the region to maximize the total volume of the objects. The mathematical models involves binary variables. This determines whether an object belongs to the selected subsets, and placement conditions. Inequality specifies whether an object satisfies the placement conditions relative to the boundary and to other objects. The problem is tackled in two stages. The first stage is subset enumeration, identifying possible subsets of objects. The second one is placement optimization, that is determine the best placement for each subset within the region. By adopting the model to these specific scenarios, we can achieve precise and effective object placement, enhancing therapeutic outcomes and advancing biological research. Hammer knife treatment involves directing beams to a common center to create a radiation dose. The primary geometric difficulty in this treatment involves precise positioning, a series of spheres within a three-dimensional tumor of varying shapes. Significant sphere overlap can lead to excessive dosages, whereas controlled minor overlap is generally acceptable. In this case, the objects are spheres with given radii. The placement region is considered as a convex polyhedron defined by a system of inequalities, where the normal equations of planes describe the boundaries. Angles can be omitted, and the specific parameters regulate the placement and overlap of these spheres. We use negative values of conditions parameters. The sequential addition scheme is realized to solve the problem. We consider a polyhedron with 12 vertices. Placement of 15 spheres was obtained. Purely placing photocoagulates microburns on the retina is a key geometric task. The photocoagulation must be evenly distributed within the edematous area, avoiding contact with blood vessels and healthy regions. Significant overlap of photocoagulates can lead to excessive dosages, whereas controlled minor overlap is acceptable. Microburns on the retina can be modeled as equal circles within a given radius. A minimum allowed distance is specified between the circles. The placement area can be divided into polygons, reducing the problem to several subproblems. According to the problem formulation, the circles have a given radius and the angles can be omitted. Parameters define the minimum admissible distances between circles. The placement region is considered as a convex polygon defined by a system of inequalities, where the normal equations line describe the boundaries. The sequential addition scheme is realized. The selected subregion is quadrilateral. Parameter is the distance between circles. The placement of 21 circles in the convex polyhedron, being a subset of the placement region, was obtained. The next application is brachytherapy. To achieve precise placement of cylindrical radiated capsules during brachytherapy, it is necessary to evaluate both the location and orientation relative to the target tissue. These parameters directly affect the radiation dose developed to each point within the treatment area and help reduce exposure to surrounding healthy tissues. Correct positioning ensures that the radiation is concentrated on the tumor, avoiding unnecessary exposure of healthy tissues and improving treatment effectiveness. In this context, the objects are equal cylinders with given radius and height. Angles specify their orientation. Parameters define the minimum admissible distance between cylinders and to the boundary of the placement region. The placement region is considered as a convex polyhedron defined by a system of inequalities, where the normal equations of planes describe the boundaries. The problem is solved using a sequential addition scheme, where the cylinders are approximated with convex polyhedrons and normalized phi functions are used. This approach ensures optimal placement of the cylinder within the treatment area. A placement of 20 cylinders in a cuboid was obtained. The next application is modeling of chromosome territories. Chromosome territories can be represented as overlapping ellipses within the nucleus, which is approximated by a convex polygon. To model these territories, it's necessary to accurately simulate the spatial distribution and interaction of these ellipses. This involves evaluating this position and overlaps to reflect the actual behavior of chromosome during interphase. The ellipses have specific half-axis, length, and height. Rotation angles specify the orientation. Parameters define the minimum visual distances between ellipses and to the boundary of the placement region. The polyhedron is presented as a composition of two convex polyhedrons. Placement of 10 ellipses was obtained. Conclusions. This investigation proposes the development of intelligent technologies in the domain of geometric design. These technologies utilize advanced methodologies and instruments to automate and optimize the placement of geometric objects in space. The optimization achieved by applying these technologies to solve practical problems in medicine and biology, improving artificial intelligence in other innovative approaches to achieve optimal solutions. The proposed universal the proposed universal mathematical model, which utilizes normalized phi function, addresses both continuous and combinatorial aspects of packing problems. The model formulation includes the distances and the orientation of geometric objects, ensuring precise management of their placement. This approach allows for the modeling of objects at a distance and controlled overlap, um, making it adaptable to diverse scenarios. The model's ability to handle various geometric shapes and placement constraints highlights its potential to address a wide range of problems. Thank you very much for your attention.